reason that these curves plateau on this end are because your ionized form of the drug is forming a salt, and then when its solubility then at the plateau region, so that's at the low region for a base and at the high region for an acid, because it's forming salt, the salt is what's precipitating out of the solution. So the solid phase, you're looking at the solubility of the salt form of the drug, and that's why it's plateauing. But when it's in its unionized, or it's the free base for the acid, or it's unionized for the free base form for the base, or the unionized form for the acid, its solid is just that acid or base. It's not forming a salt. But these are in here just to explain why it plateaus, but I won't ask you these for the exam. So if you want to learn them, feel free. So no, it just means that once you start to form the salt here, the solubility isn't changing any longer with pH, because it's just forming a salt, and that's why it's plateauing. So you're only looking at these ends of the curve. That's what the KSP is telling you. KSP is the solubility of the salt. So you're no longer looking at the drug itself. You're looking at the solubility of the salt form of the drug. Okay, so the next lecture was the chemical and physical stability lecture. So remember when I went through this lecture, I just briefly talked about physical stability, and for this exam, I won't really be asking about physical stability. Because physical stability is more driven by different administration routes and dosage forms that you use. So you should have gotten a lot of physical stability in Dr. Ferris's lectures. You're going to get some more in Dr. Geary's lectures. So I focused mostly on chemical stability of drugs in my lecture. So remember the four main types of chemical stability that we went through, right? They were hydrolysis, oxidation, bastization, and photodegradation. So those are the four main routes of degradation that we'll be looking for. So remember, for these kinds of questions, I asked questions about looking at the actual drug structure and being able to identify what potential routes of degradation it might go through, and then also ask questions about how the pH might affect the degradation of the drug. So first, we'll look at hydrolysis. So remember, hydrolysis, when you're looking at the chemical structure of the drug, this one's easy. You're only looking for esters and amides. So if you have a drug that has an ester or an amide, it means it's susceptible to hydrolysis. And then remember, we looked at the comparison of rates of hydrolysis of these. And I told you that esters have higher hydrolysis than amides that are in a beta-lactam ring versus amides that are open, not in a ring structure. So just remember that how you compare those. So remember, the esters have higher hydrolysis rates because you have an oxygen here, which is better able to stabilize a negative charge as it's getting degraded. So esters hydrolyze faster than beta-lactams, but hydrolyze faster than amides. And remember, we looked at different structural differences between how the rates of hydrolysis occur. So increased rates of hydrolysis are seen under extreme acid and base conditions, because an acid and base catalyze hydrolysis. If we had electron withdrawing groups in any of these positions, remember, we increase the rate of hydrolysis, right, because it's pulling away from this carbon, making it more positively charged. And then when you have ring strain, like a small ring, like a 4-membered beta-lactam ring, we also have increased rates of hydrolysis. So that it's increased compared to an amide that's not in a ring structure. So decreased rates of hydrolysis we see at more of a neutral pH between 4 and 6. If you have electron doping groups in those R positions, so remember, they're pushing electrons towards this carbon, making it less susceptible to nucleophilic attack. And then if you have bulky groups in these R positions, because they sort of block the nucleophile from being able to access that carbon that's getting attacked. So when you have a formulation, you're making a formulation for a drug that you know is susceptible to hydrolysis, meaning it has an ester and amide in it. You would want to try to avoid or reduce exposure to water. Formulate at a pH of 4 to 6, right? Because that's when we slow our rates of hydrolysis. And then store at a low temperature. Remember, when we increase temperature, we increase the rates of hydrolysis. So oxidation. For oxidation, the groups that you're looking for in the structure are phenols. Remember, so that's a benzene ring with a hydroxyl group attached to it. So you're looking for phenols, you're looking for aromatic and tertiary amines, sulfhydryl and thioether groups. So if you're looking at a chemical structure, it has one of these functional groups in it, then you would say oxidation is possible for this drug. And then the formulation considerations for oxidation are, of course, avoid exposure to air. Sometimes you can add antioxidants to the formulation. Metals, remember I said metals will catalyze oxidation processes, so you want to avoid metals. And metals are present usually in different excipients that you might add to the drug formulation. Avoid exposure to light. So remember I also said that light can also catalyze oxidation. So you want to avoid exposure to light for something that might oxidize. And then I showed pH rate profiles for both of these types of degradation. So remember, for hydrolysis, you get this typical V-shaped curve. So it's going to center around a pH of 4 to 6. So that's your maximum stability. And then if you have any bends in the curve on either one of the sides, that means that you just have a neighboring ionizable functional group somewhere in the drug molecule. For oxidation, remember I said that you get increased rates at basic pH. So your ionizable functional groups you're looking at are the phenols, right? So remember, when you increase the pH for an acid, you're increasing ionization, and phenols tend to ionize or to oxidize faster when they're ionized. So that's why you see an increased rate for increased pH for phenols. Amines are the opposite. So amines will oxidize faster when they're in their free base form. So increasing pH means you're increasing the amount of the free base form. So both of those, phenols and amines, will have a pH rate profile that looks like this. So where this falls on the pH range, it's hard to guess. You kind of have to look at the experimental data, so I would never ask you where this pH starts to increase for oxidation. I would have to show you the graph, or you would just know that for oxidation you're avoiding high pH. Okay. So racemization, remember what you're looking for racemization. First you need to find a chirocarbon. So a chirocarbon is a carbon that's attached to 4 different substituents. That means it's a chirocarbon. So first you're looking for a chirocarbon. Then when you're looking at that chirocarbon, you want to make sure that one of its 4 substituents that are added to it is a hydrogen. So one of the 4 has to be a hydrogen, and then one of the other 4 also has to be either an aromatic ring or it has to be a carbonyl. So it has to fit all 3 of those criteria for it to be susceptible to racemization. So just identifying a chirocarbon by itself doesn't mean it's going to racemize. It has to be a chirocarbon with a hydrogen attached and also attached to one of these 2 structures. And for racemization, we also protect those from light, because remember I said light can catalyze racemization. So for formulation considerations, we're just protecting those from light. For photodegradation, that one's pretty easy. All you're looking for are double bonds. So if you see something that has a lot of double bonds, like carbon-carbon double bonds, which are alkenes, or you see a lot of conjugated aromatic ring systems, what that means is you have a lot of aromatic rings that are kind of stuck together. Those are conjugated ring systems. So you're looking for double bonds, conjugated ring systems, so you say those might be susceptible to photodegradation. And then as I already mentioned, remember light can also catalyze oxidation and racemization. So those 3 types of degradation, oxidation, racemization, and photodegradation, we're protecting all of those from light. Hydrolysis, light doesn't do anything, so we don't care about light for hydrolysis. But for the other 3, those are just protected light.
One question on racemization. so eventually you have to have a chiral carbon attached to a hydrogen. And the third is to have an aromatic ring, or could it be a non-aromatic, or it has to be aromatic?
It has to be an aromatic ring. The reason that it happens is because when you have an aromatic ring or a carbonyl like this, it's also pulling electrons away from this carbon, the chiral carbon, and it makes it more susceptible to change its orientation. So it has to be aromatic. So a non-aromatic ring probably wouldn't affect racemization.
So do all then racemizations also go under photo, because this has a double bond and it's aromatic?
So for the case of the molecule on the left, yeah, you can say probably photodegradation and racemization for that drug.
Oh, thank you.
So that was chemical degradation. We got chemical degradation? Yeah? Any other questions about it? So remember for that one, I might just show a drug molecule and say like, how might this degrade? And it would just be a matter of looking at the structure and identifying the susceptible functional groups, and then also knowing what those formulation considerations would be in response to how the drug might degrade. So if it's an alkene, maybe, because alkenes are very susceptible, but if you just see one aromatic ring, usually you wouldn't say photodegradation. It usually has to be like multiple aromatic rings stuck together. But if you were in an exam to identify like something that has one double bond as photodegradation, it would be, I would say it's correct. I can't say it's not possible because it's possible. But generally, if you're really just looking for the degradation, you're looking for a lot of double bonds or a lot of ring systems. Usually if you just say see one or two, you would still have to test it for photodegradation, but it probably wouldn't matter too much. So next lecture was rates of degradation. So remember in that lecture we did a lot of looking at the different rate equations, right? And I'm not going to ask you about rate equations. We went through those so that we could really just get to this equation here, looking at how to estimate shelf life or T90 values. So for rates of degradation, you would just remember rates will increase when you increase temperature. So when you're looking at hydrolysis, oxidation, racemization, photodegradation, they will all be higher, degrade faster when you increase the temperature. But remember, I also mentioned that when we're looking specifically at racemization and photodegradation, those aren't necessarily linear related to temperature. Remember when we talked about looking at hydrolysis as a route of degradation, we could use the Q10 method to look at the shelf life at different temperatures, and that was because the relationship between degradation and temperature is linear for those types of degradation reactions, but it's not linear for racemization and photodegradation. In other words, in an exam, I wouldn't give you something that's going to degrade by racemization and ask you to calculate the degradation at different temperatures. Really only for hydrolysis we're using those Q10 methods. So we also talked about the order of reactions. So we had the main two orders of reactions for pharmaceutical products are pseudo first order and first order reactions. So that's mostly chemical degradation in solutions. And then we also had zero order reactions. So the zero order reactions are concentration independent, and that's mostly what's occurring when you have chemical degradation in a suspension. So first order, we're looking at concentration dependent degradation in the solution. Zero order are concentration independent in the suspension. So we can calculate the shelf life of chemical degradation reactions using this equation here. And then the shelf life, remember, it's the time that it takes a drug to degrade by 10%, so that's why it's called T90. It's the part where you have 90% of the drug remaining in the formulation. And then for these, you just have to be careful to use the right one for the right order of the reaction. So if I give you something that's in a solution, you would be using the first order. And if I give you something that's in a suspension, you would be using the zero order. And one way to double check to make sure you're using the right one, if I give you a K value, and the units of the K value are just 1 over time.